Some of these more complicated circuit problems you can actually do without thinking too much about Kirchoff's rules, the loop rule and the junction rule. Those equations that we use for equivalent resistance, either in a series circuit or a parallel circuit, those are actually derived in part using those two rules. And so if you're just using those equations, you can actually do some of these more complicated circuits. Where that falls apart, though, one place that falls apart is if we have multiple batteries in a circuit, or if we had batteries, even just a single battery in a circuit, but have our resistors in sort of an odd configuration, something where we don't have really a straight parallel or a straight series circuit. So maybe a triangle of resistors where each point on the triangle is attached to something else. That can throw things off. So this is where we need to use the more general loop rule and junction rule that Kirchoff describes to solve these problems. We can't rely on just the equivalent resistance. So let's try one like that. A circuit like this doesn't seem especially complex. We have all our current leaving the 8-volt battery going through that 100 ohm resistor, and then it splits into two paths here, and it's only two paths to worry about, and each path doesn't even split into further paths, so it doesn't seem too bad. It looks at first like we could just take the 200 and 300 ohm resistor, and those are in parallel with each other, so we'll combine those and find the equivalent resistance, and we've already made a mistake at that point. The 200 and 300 ohm resistors are not in parallel with each other. In parallel with each other would mean that both ends of those resistors are connected to each other. Now, this end of this resistor is connected to this end, but this end is not connected to this end. We have a battery in between. So we could say that this branch of our circuit and this branch of our circuit are in parallel, but we've got this battery that throws things off there. So we do have to look at the more general loop rule and junction rule to solve this one. We can't just go with equivalent resistance. So a few things that we can do with the loop rule and the junction rule, but all of them are going to require us to use different values for delta V and for I, the voltage drops and the currents. So I think it's helpful on these ones to just start by labeling some of these quantities. So I'm going to have current flowing out of the battery, and up until this point it's all together. I'll call that I1. And then that same amount of current flows back into the battery, I1 there. And then at this point here, we have, this point right there, we have a split. And some of our current goes down this path, and some of our current goes down this path. And so we need to show that we won't have all of our current going through each of these. Let's make that I2. There we go. And this one we can have as I3. And then I2 and I3 together have to be the same as I1. That's a junction rule. Let's go ahead and write that out. I1 has to be equal to I2 plus I3. The current that we have, it just splits up. So we don't have extra current because we have an extra path. We don't have less current. We don't have these moving charges disappearing when we have that breakup. We only have a split. And so the totals have to be the same before and after the split. And then the other thing I like to do here is label my voltage drops. And so let's call the voltage drop across this resistor, that can be delta V1. Delta V2 can be across this resistor. Delta V3 can be across the last resistor here. And I don't bother labeling the voltages on the batteries as variables, since we already know the numbers there. We can just throw the numbers into the equations. All right, so now into our loop rule stuff. The loop rule says that for any path that we go around this circuit, our total change in potential has to be 0, or our total voltage drop or our potential difference has to be 0 for any complete loop. So there are two complete loops that I can have my current go through here. If I start right here at the battery, We can go through the battery and then through this resistor. There's no other options up until this point. And then we have a split. So some of our charges will flow through this resistor and go back to this battery. And so the total voltage drop across all three components here, the battery, this resistor, and this resistor, has to give us 0. So we can't have infinite energy or energy disappearing as we go around this loop. And then the same can be said for the other path here. We can go from here over on this path and down this direction. Now there's actually a third loop that we could look at here, and that's the loop that just involves this little part of the circuit. And so you can start out here and go this direction. You could actually start out and go the other direction as well. We're only going to need to do 2 of those loops though. So we'll do this one and this one, always going through this 8-volt battery. So let's write out loop rule equations for those then. So the loop rule equation just says that the total change in V has to equal 0 for any loop. So for that first loop I described, we start out with, let's start just before our battery. So first thing we hit is the battery, and that takes us up by 8.0 volts. And then we're going to go through that 100 ohm resistor, and so that's going to take us down by some amount that we call delta V1. And then we go through that 200 ohm resistor, and that'll take us down by some amount that we call delta V2. Now, I don't know delta V1 or delta V2, but I do have Ohm's law, which can be written as delta V equals I times R. And I know the resistance for each of those 2 components, so we might find it more useful to write this out as still plus 8.0 volts to start with, and then minus, instead of delta V, I'll just write I times R, but it's got to be the current through that resistor and the resistance of that resistor. So this would be, see, the current there is I1, and the resistance of that is 100 ohms. And then same thing over here, just a negative. The current through that 200 ohm resistor, that's I2, and the resistance is 200 ohms. It has to add up to 0. Okay, well I can't do anything with that equation. There's 2 unknowns and only 1 equation right there. So, now we start looking at other equations. I have another equation here, I1 equals I2 plus I3. That doesn't help me though. Now this one has 3 unknowns in it. This one only has 2 of that. So I've got 3 unknowns but only 2 equations right now, which means I can't solve. I need 3 equations if I'm going to solve for 3 unknowns. So let's write another loop rule equation. We did the loop through this 200 ohm resistor. Now let's go through this 300 ohm resistor and through this other battery. And so for that one, we'll start in the same place. So another total delta V has to equal 0. We'll still go through that battery first, 8.0 volts. We'll still go through the 100 ohm resistor, so plus a negative delta V1. Then we're going to go through this other battery, the 6-volt battery. And when we went this direction on the 8-volt from the short line side to the long line side, we go up by 8 volts. On this one, we're going from the long line side to the short line side. So we go down by 6 volts. This is on a battery. This would be the negative side, and this would be the positive side. And so we can have current going through in either direction on a battery, but the battery is either going to help our energy on these, it's going to add to the energy for these electrons, or it can detract from the energy. It can take away some of that energy. All this 6-volt battery does is maintain a constant potential difference between this point and this point. And then we use the long and the short lines to show which side is the higher side and which side is the lower side. So on this one, we're going from long to short, so that means we're actually going to be decreasing in voltage. So that would be plus a negative 6.0 volts. And then we go through the 300 ohm resistor, and we called that voltage drop V3. So that's plus a negative delta V3. And we'll do the same thing that we did just a minute ago with this, where we rewrite the delta V's as I times R. So plus 8.0 volts plus a negative, and that was I1 times 100 ohms, same as it was up above, plus a negative 6.0 volts, plus a negative, and that's I3 going through that 300 ohm resistor. That total has to equal 0. All right, now things are looking a little better. We've got one equation, two equations, three equations, and they have all the same three unknowns. We have I1, I2, and I3 as unknowns. So at this point, we are dealing with a math problem. We have a system of equations that we need to solve. So really, the physics thought part is done for a little bit. Now we just have that process of solving a math problem. So I think on something like this, you have a variety of options for solving. Probably the method that most of my students use would be solving by substitution. So let's look at how to do that now. So now we have a system of three equations with three unknowns, and we need to solve the system. In particular, on this one, we were asked for the current through the 200 ohm resistor, and we labeled that as I2. So I need to work with, eventually, an equation that has just I2 as an unknown, and then solve for I2. So as I do my substitutions, I'm going to keep that in mind just so I don't accidentally eliminate I2 from my equation. If I do, it's not a big deal. We'll solve for the wrong variable, then have to take it back to a different equation and plug in that number that we get to I2. But it's less work if we solve for I2 as our first numerical solution. On this one, I see that the two equations on the right each only have two variables in them, so that makes them a little easier to work with, but they're not the same two variables. So that's my first step, is I'm going to try and use the very first equation. I'm going to plug that in somewhere in either the second or the third equation to make it so that the second and the third equation both have the same two unknowns in them. And so as far as unknowns go, I could plug in I1, instead of I1, I could write in I2 plus I3 for everything. It's already set up that way. The only downside to doing that is I have to do that substitution both here and here. So that makes me less likely to want to do that. I could rearrange this one and make it, say, I2 equals I1 minus I3, and then I'd only have to plug that one in here. So that's nice. But then I'm left with this equation and this equation both not having an I2 in it, because this I2 would be replaced. I2 is what I'm looking for, so I eliminated the variable I'm trying to solve for. So my other option then would be to rearrange this one for I3. That'd be I1 minus I2 equals I3. And then over here where I have I3, I'd put in I1 minus I2 instead. And then once I simplify these two equations, I'll see that I have just two equations with just two unknowns in them. The two unknowns are going to be I1 and I2. And then from there, I can work to get it down to just a single equation with a single unknown. So let's start over here. We needed to rearrange this one. So I want to get I3 by itself. So I3 is going to be equal to I1 minus I2. And then my first substitution is going to happen over here. There we go. While I'm at it, I see I have an 8 volts and a negative 6 volts here, so I'll combine those. That's 2 volts, positive. And then minus I1 times 100 ohms. And then minus, and instead of I3, I'm going to do I1 minus I2. That was what I solved for over on the very first equation. Times 300 ohms equals 0. Okay, and now I see that I have I1 in two different places in this equation, and so that's kind of a pain. Let's simplify this by combining like terms as much as we can. So I have 2 volts minus I1 times 100 ohms. And then minus, and I'm just going to factor this out. So we'll have 300 ohms times I1 and minus 300 ohms times I2 equals 0. Now I have two different terms with I1 in it. So it's 2 volts minus I1 times 100 ohms. Oops. And then minus I1 times 300 ohms. Switched my order up here, so let's fix that. And then minus a negative 300, so plus I2 times 300 ohms. Okay, so then I've got the negative I1 times 100 and the negative I1 times 300, so that'll be 2 volts minus I1 times 400. Plus I2 times 300 ohms. And that's equal to 0. All right, let's reevaluate our situation here. We've now got two equations, the second and the third equation. They both have the same two unknowns, I1 and I2. I need to isolate I2 in an equation where it's the only variable. So I need to eliminate I1 from both of these equations. And again, I can do that with a substitution. There are other methods as well, but substitution seems to be the way that most of my students have been most familiar with. So let's go ahead and do another substitution that we're going to use to get rid of I1. Now, I see I1 is multiplied by 100 ohms on the left side and by 400 ohms on the right side. So either I could change both equations to make them both have a 400 ohm in there, or both have a 100 ohm in there. So for example, I could multiply every term here by 4 on the left side and on the right side, but 0 times 4 is just 0. And then substitute that way, so I'd have I1 times 400 being replaced. Or I could just isolate I1 in this equation, or isolate I2 in this equation, and then plug in to the other one. Either way will work just fine. I'm going to go ahead and multiply this equation by 4. So that'll be plus 32 volts plus a negative I1 times 400 ohms, and then plus a negative I2 times 200 ohms equals 0. Running out of space there. All right, and then it doesn't really matter which direction I go for substitution here, so I'll rearrange the equation on the left. So that'll be 32 volts minus I2 times 200 ohms is equal to I1 times 400 ohms. Oops. Okay, and then on the right side I have I1 times 400 ohms in there. I'm going to replace that with 32 minus I2 times 200. So 2 volts minus 32 volts minus I2 times, oops, I already forgot what I needed to plug in there. I2 times 200 ohms. Okay, so that's just taking the place of this I1 times 400. So then I also need to do the plus I2 times 300 that's up above. Equals 0. All right, I'm down to an equation with a single unknown, so let's finish this one out. Let's see, I've got 2 volts minus 32 volts. Oops. And then plus I2 times 200 ohms. And then plus I2 times 300 ohms. So this would be a negative 30 volts plus I2 times 500 ohms has to equal 0. I2 times 500 ohms has to equal 30 volts then, adding that 30 volts to both sides. And so I'm going to get, for my final answer, after all this substitution work, 30 volts divided by 500 ohms, which gives us an answer of 0.060 amps. Okay, so as you can see on this one, a lot of the work happens, after the physics part is really done. We have just the math part of solving those equations. So 0.060 amps is what we end up with, and we ended up with that result. We were able to get to that result by using Kirchoff's loop rule and Kirchoff's junction rule. And the loop rule, remember, we had to write two different equations with that. We had 3 unknown currents. We needed 3 equations. So we had a junction rule, and we had 2 loop rule equations. Thanks very much for watching. If you learned something from this, please like or share the video so other people can find it as well. If you think you'll learn something from future videos like this, go ahead and hit that subscribe button. Thanks again.